Okay, welcome back to my YouTube channel on the Chem 1331 lecture series. Uh, Today we're going to talk about the ideal gas law and gas laws in general and in chemistry. Gas laws are very important because first of all they tell us something about the intermolecular, interatomic nature of interactions. And it also was an important defining point in defining basic atomic theory, and also many chemical reactions occur in the gas phase themselves. And so, understanding how volume changes, temperature changes, and pressure changes affect chemical reactivity is highly important in our study of chemical processes. So, this is chapter 8. This is going to be material that will be covered on the next and upcoming exam. It also forms the basis of much of what we discussed in later topics of thermodynamics, which I don't know if we probably won't cover in this class, but certainly in the next class we will, and so on. And the basic equation that we're going to learn about today is what's called the ideal gas law. And the ideal gas law, sorry about the focusing of this, my webcam is having a hard time focusing today. Just not focusing on things. Just doesn't want to focus at all today. How about that? There we go. That's a little bit better. For whatever reason, it is not focusing. There we go. The ideal gas law. And the ideal gas law is what's called an equation of state. And what an equation of state is simply a relationship between the energy, which is pressure volume, and some sort of function of the temperature. Is your basic idea this is a bracket, not a C. Some function of the temperature. And the ideal gas law specifically is that it is equal to some constant times the temperature. And that constant is specifically the number of moles in the system times the gas constant times T. So N is the number of moles, R is the universal gas constant, which I'll introduce later, and T is the temperature in Kelvin. Okay, and the ideal gas law is important because it is the limiting behavior of all real gases at low pressure. Okay, so if you have your own theory of gases, and again, sorry about the lack of focus. I'm not too sure why this camera is misbehaving today. But any real gas must approach ideal gas law behavior as the pressure becomes very, very low. And we'll talk about some of the assumptions of the ideal gas law today and the next time. But I want to move on. So in the ideal gas law, so the topics we'll talk about today are pressure, the gas laws of Boyle's, Charles, and Avogadro, the ideal gas law, which I've just mentioned, issues of stoichiometry, partial pressure, kinetic theory of gases, diffusion in real gases, and characteristics of several gases, and so on. We will probably not talk about the thermodynamics of gases, which are very important for later studies of thermodynamics and work and expansion and contraction of gases. So let's move on. So the first thing is any gas, and what defines a gas is simply that in a gas, a gas expands to occupy all available space. So its density So the density of a gas is uniform throughout the volume. Okay, that is simply to say that I don't have the case where if I have a volume, I have the same probability of observing a gas, n numbers of gas molecules in that little volume as I do in this little volume over here. That's not the case in a liquid. For example, if I had a liquid, I have on average 3 gas molecules in that little volume. I would have on average 3 gas molecules in that little volume over there. But in a liquid, that's not the case. In a liquid, if I have a volume, let's see, here's my volume. I might have a liquid that only occupies, half the volume, right? So I could have liquid down here. I could have gas up here. In a liquid, doesn't occupy the entire volume. It conforms to the shape, but it has a definable boundary between the liquid and the gas, and so it's more dense down here and less dense up there in the gas phase and then in the liquid phase. And so that defines a liquid. Of course, a solid is going to be something that keeps its form. So a gas is uniform throughout all of volume. It mixes completely. If I have 3 different kinds of gas molecules in the system, I will have a uniform mixture of all 3 of those gases throughout the system. And the last thing that it does, it exerts pressure on its surroundings. So a gas is very low density, and it exerts pressure because as a gas molecule collides with the wall, it rebounds, and it exerts a force on the wall. So this is a gas molecule rebounding off the wall, exerting a force, and as this thing ricochets around inside of the gas, this confining volume, it exerts an outward force, and it's the counterbalance between the forces of, let's say, the atmosphere pushing in and rebounding off, and my gas molecules that are trapped inside, let's say, for example, a balloon that are rebounding and pushing off, that keep an outward pressure on the walls of this container. And of course, if it's static, there's an inward pressure due to the outward atmospheric pressure of the system. So if you have a balloon, here's a little cartoon of a balloon, right? And I have some air molecules inside of the balloon. It's rebounding and pushing off against the walls of this balloon. Okay, and likewise outside of the balloon, I have air molecules that are bouncing off and pushing in and doing their kind of thing. And it's the counterbalance of these 2 forces that leads to the equilibrium shape of that balloon. But it's not because the fact that I have a packing of the gas molecules inside the balloon. It's simply that the gas molecules inside the balloon are moving around. They exert a pressure on the balloon, and so consequently we can say, well, as I increase the velocity of the atoms inside the balloon, well, I collide with the surface of the balloon more often, and so perhaps I should be able to say is that pressure is then proportional to the temperature of the system, because as I collide more, i.e. increase the temperature, I must increase the pressure. So our first gas law that we can empirically define is that pressure is proportional to the temperature. Okay, that's our first simple gas law. Now, how do we measure pressure of a system? Well, if we look over at the PowerPoint slides, we have an example of how we do this, and we use what's called a barometer. And a barometer is simply a counterbalancing of forces. So you have air molecules pushing down on the surface of the mercury here, which is exposed to the air, and to make a mercury barometer, I take a tube of mercury, completely fill it, and plunge that bottom into a dish of mercury. There's a mass of mercury here, pushes down, and there's of course air on top of this which is pushing up, and so there's a counterbalance at some point. And when this mass is equal to or the weight of this mercury is equal to the pressure being applied, that's the system comes to equilibrium, and I read off how much mercury is in this tube. And the standard atmosphere is 760 millimeters of mercury. Now 760 millimeters is about 2.5 feet, and so clearly this is not something we're going to carry around with us very often. Not only that, mercury is a volatile liquid, and mercury isn't such a good thing to breathe, and so these are not used very often in the laboratory outside of maybe a physical chemistry laboratory that's interested in making very standardized measurements of the of pressure, for example. But that is what's defined as the standard atmosphere. 760 millimeters of mercury is the standard atmosphere. Okay. Now you can make your own in ways. I'll show you how to do that. And this is the common way that we do this. 1 millimeter of mercury is also known as a torr, named after Torricelli, and 1 standard atmosphere, which is like I said in our discussions of enthalpy and other thermodynamic quantities, we need to define a standard if we're going to make thermodynamic measurements. And the standard that we use is 1 atmosphere. A standard atmosphere is equal to 760 millimeters of mercury, 760 torr, and that is a pressure. And the pressure is, of course, force divided by unit area, and I can convert this into pascals if I wish. And in the SI unit, the force is a Newton, unit of area is a meter, and the unit of pressure is newtons per meter squared. It's called a pascal. And 1 standard atmosphere is 100,000, 101,325 pascals, or 1 atmosphere is 10 to the 5th pascals. Okay, and that's just simply a definition. So a manometer is used to measure the pressure of gas inside of a container, and again we do this in a very simple way, similar to what we would do with the atmosphere. I have a standard atmosphere which pushes down on an open end of the mercury, and the gas inside, just like the walls of our balloon, exerts a pressure on this side of the mercury, and I look at the differences. This is going to be more pressure, or I should say this would be a lower pressure than the atmosphere by how many millimeters of mercury is represented here, versus a higher pressure gas which pushes down on the atmosphere by this many millimeters of mercury. So the one way we can do a chemical reaction in the gas phase is to have a little closed tube, and I monitor the pressure in terms of changes of millimeters of mercury inside of this container. Now I can do this in all sorts of different kinds of geometries, but basically the general approach is I measure the pressure difference as a chemical reaction or some sort of change occurs over the course of an event. Now this could also be done in the following way. So just because I want to make sure that people are actually check to see, first of all I want to see who all is doing this, and sort of as a way to occupy your time, if you would, at home. I'm going to challenge you all to, first of all, subscribe to the YouTube channel. You get a point of extra credit for doing that. I can note that in the subscriber list on the YouTube channel. I think right now there are 4 people subscribed, and there are 50 people in the class, and I think most of those 4 are not people in our class. But anyway, if you subscribe, you'll get automatic updates to the content that I'm posting, and that way it will help you prepare for the upcoming exam and the upcoming homeworks. Second of all, I'm going to give you a challenge to make a barometer at home, and there's a picture that I put down here in the PowerPoint slide. of one way to do this. There are many, many ways of doing this. This is something, again, you can do at home. But do this. This is simply a cup, a board, a balloon, maybe a chopstick, or maybe some sort of like skewer, and a card that's gradiated. You could put a ruler here if you wish, and just measure over the course of a week or so how this rod goes up and down. Correlate it with the weather, and so on. If you want, you could even correlate it with the room temperature, and to see that what we're talking about really has nice applications. This is something you can do. Probably have done it already as a high school science fair project or a grade school science fair project, but do this as a way to do some at-home experimentation. Send it to me by April 11th, and I'll give you a point of extra credit. Okay, so let's go back to the content. So the interactive, so here's what this is simply how to convert torr to atmospheres. And 49 torr, and I'm going to represent this as atmospheres. So simply divide it by 760, the standard atmosphere, to get it in terms of atmospheres, or I multiply it by 101,325 pascals to put it into units of pascals. Simple unit conversions. Again, as I talked about in class, it's important to keep track of units as you do these calculations. So cancel units and make sure that you get the right unit. At the end, you will get, chances are, unless you plug something into your calculator wrong, you'll get the right answer. And again, we want to emphasize accuracy and all that, but it really is a really good practice to make sure that you get the correct units that you want on the other side of the equation. Okay, so the first thing is of course, these were things that were discovered historically, and Boyle was an 18th century natural scientist. I don't think they were called chemists or physicists at that time, but he's a natural scientist, and he did measurements of pressure and volume, and noted that for the most part, that pressure times volume at the same temperature was equal to a constant. So Boyle's law is, again, that pressure volume is equal to some constant. Now this is at some temperature T. Now this looks very familiar what I just wrote down. So pressure times volume is an energy, and K is some constant. And again, this is at some specified T. And so what Boyle's law says is that this is something that it doesn't matter. This is a constant. This is a constant at some fixed temperature. So therefore, if I change pressure and volume, pressure 1, volume 1 must be equal to pressure 2, volume 2. So this is for example, at some constant temperature, some initial pressure, some final volume, or some initial pressure, volume, final pressure, volume. These two are related to each other. Okay, and a gas that obeys this particular law is an ideal gas, and we'll discuss what an ideal gas has. This is an ideal gas. Okay, so an ideal gas is a gas. First of all, it's a gas that obeys Boyle's law, which seems like a circular reasoning. But ideal gases, an ideal gas obeys the ideal gas law. Now, it's ideal in the sense that it is, no gas really obeys the ideal gas law. It's a limiting behavior. You know, again, I can't quite get this thing to focus right today. I think maybe it's a light setting. It's just not getting the focus right. Maybe that's a little bit better. Sorry about that. I'm not too sure why. This is a high-grade camera. It's just not coming out. Okay, the ideal gas law is that pressure times volume is equal to some constant, but that constant can be written in the following way. Again, K is some constant that it's a different constant here. This is some constant that I'm going to leave like this. Maybe I should write this as a capital K. It's some constant that looks like this. So the ideal gas law, K, is going to be a constant that doesn't depend upon temperature. This K did depend upon temperature, and and this is what's called an equation of state. An equation of state is simply a relationship between pressure, volume, and the temperature of the system. And the equation of state depends upon the interactions that go into this, and it's very predictive. It says that what is the pressure volume of a gas at a given temperature, or other things that might go in. But the ideal gas is important because it assumes that the following, that the gas molecules, gas atoms, occupy no space. Okay, they're point-like particles that carry mass but occupy space. And remember, this is an assumption. We know that's wrong, and that they do not interact. Okay, they don't interact. So that is wrong because we know that atoms and molecules occupy space, and they interact with each other in the following way. They repel each other at short distances, i.e. they occupy space, and they attract each other at long range. And so the ideal gas law is okay. So ideal behavior is the limit where the pressure goes to zero. And when the pressure goes to zero, I have essentially an infinite space between the atoms. They really don't interact with each other at all. And the fact that there's a volume of space doesn't matter. And so all real gas laws must give the ideal gas law in the limit that the pressure goes to zero. Okay, so that's a key theoretical construction that we must see for any real gas law. And there are many real gas laws. Okay, so Boyle's law is one. So in Boyle's law, if we do a Boyle's law experiment, we plot. Whenever you do an experiment, you want to plot the data. So one of the things I want to point out with this is maybe a little bit of confusion, is that if I do a Boyle's law plot, what we expect, well, P, pressure times volume, is some constant. So if I plot pressure and versus volume, I should get that pressure is equal to whatever constant it is divided by the volume. Right? So if I get something that looks like that, if I plot this like this, right? So as I double the volume, I half the pressure. Doubling the volume, I get half the pressures, right? I double this, I get this. So if I remember that P1, V1 is equal to P2, V2 at some constant temperature. So if I double the volume, I get half the pressures. Put that up there. Double the volume, half the pressure. Now, a better way of, and you can get experimental data, which is shown, for example, on the PowerPoint over here. Now, a better way of doing this experimentally is to make a plot in the following way. So we can plot volume versus 1 over the pressure, or vice versa. It doesn't matter. But the issue is if I will get a slope that would go like this. Now, the key of this, and the slope is this PV is equal to constant, right? The slope is therefore going to be that constant. the key is when you make a linear plot of experimental data, it isn't simply a matter of convenience. Because with modern plotting techniques and software, this is just as easy to plot as that, right? This you can you could plug this into an Excel spreadsheet and plot out that data easily enough, or this data, it doesn't matter. And so why? So the reason is if I do a fit, a least squares fit of this data to some sort of function that says that v is equal to c over p, which is also what I get, right? Because I can take this equation up here, just simply rearrange it, and use the least squares regression to fit this data to this constant. It's a far more accurate means of data reduction and calculating that constant, which is the slope, c is the slope, than trying to extract the same slope or the same constant out of this. And the reason is because the error is not uniformly distributed over this curve, whereas on this curve the error in your measurement is. And so this is a far easier, more accurate fit. So whenever you do a fit to a model, always try to make it in terms of a linear regression. This would require some sort of nonlinear regression. Now, that stated, modern techniques, modern software probably really doesn't matter so much these days, but this will still be a more accurate way of testing a model, if you want, to fit your data to some sort of functional form that you can guess. And you'll see this when you do kinetics, and you see this when you do other sorts of data analysis. Always try to use a linear scale versus trying to fit to some sort of exponential or power function type behavior. This is a far less accurate fit, whereas that is a far less accurate. It's far more accurate fit. It's unfortunate that we don't have a full course on data analysis. When I was a student, we had a very intensive course on data analysis because we're still doing a lot of our analysis by hand and without computers, and so it was important to make sure that your experiments were done as accurately as possible and that your fits were done as accurately as possible. So always try to make a linear plot, and whenever possible. And again, the reason is because you uniformly distribute the error over the plot, the error in the fit over all of the data set, whereas the error in the fit is not uniformly fit. So I wind up with a lot of freedom out here in how I can throw a curve between all of these data points. And so it's just simply it's not by convenience. It really is a mathematical reason why we want to use a linear scale. Okay, so here's an example of using the Boyle's law. Again, this is like some data here. So, for example, sulfur dioxide is a gas that plays a central role in the formation of acid rain. It's an exhaust of automobiles. Basically, what happens is that sulfur dioxide, which is again a byproduct of burning coal and burning any sort of fossil fuel, is produced. There's sulfur that's within the material itself. It burns, produces sulfur dioxide. Sulfur dioxide mixes, dissolves in water, to form sulfuric acid. It's the basic chemistry that is going on. And it's also irritating. Breathing sulfuric acid is very irritating, and it also destroys buildings and woods and coral reefs and all sorts of other kind of bad things. So, so here's the Boyle's law example. If I simply have a gas that's so many pascals, 5.6 times 10 to the 3 pascals, the pressure is changed to something. what is the new volume of the gas? So again, we can simply use P1 V1 equals P2 V2 and set this up as in the following way. Let's just write this down. So P1 V1 is equal to P2 V2. I need to solve for V2, so V2 is simply P1 over P2 times V1. Now, I write this out explicitly because I want to emphasize the fact that, again, these are two pressures, right? So the units of pressure are going to cancel out, and I get units of volume at the very end. So if I write all of this stuff out, what do I get? 5.6 times 10 to the 3 pascals divided by 1.5 times 10 to the 4th pascals. So I've increased the pressure, okay, and the initial the volume was 1.53 liters. So P1 V1 P2. Here we go. This is our equation. Pascals canceled out. I get liters at the end of the day. We can plug that into our calculator very easily and get the following, right? 0.57 liters. Sometimes we can write this as lowercase liters, but maybe it's in best is putting it as uppercase liters. Okay, so the new volume is smaller. So does that make sense? Well, it does make sense. I've increased the pressure by roughly a factor of 3, and therefore the volume goes down by roughly a factor of 3, just as a quick internal check. Okay? Very simple. Again, keep track of your units, keep track of everything as you do this. Now, another law is that of Charles, another 18th, 19th century natural scientist. And Charles noted that if I keep the pressure constant, so the Charles law, is that volume is proportional to temperature, keeping the pressure constant. And specifically, this is again one of the predictions of a gas, is that the volume of the gas, of an ideal gas, goes to 0 as T goes to 0. That's Charles' law. The volume of the gas, because in an ideal gas atoms occupy no space, the volume of the gas goes to 0 as T goes to 0. And this gives us an idea of absolute 0. So Charles' law is that volume is equal to some constant of proportionality times T in kelvins. So Kelvin equals degrees Celsius plus, well, it's actually 273.15 degrees. So that this is that is actually very important to know. So 0 degrees Celsius, the freezing point of water, is 273.15 degrees Kelvin. So 1 degree Celsius is equal to a change in temperature of 1 Kelvin. So changing the temperature by 1 degree Celsius has the same effect as changing it by 1 degree Kelvin. It's a linear 1-to-1 relationship. The size of the centigrade is the size of a Kelvin degree. Okay, so this is the Charles law, and you can see, we can do the same sort of analysis. If I have a sample of gas at 15 degrees Celsius in 1 atmosphere, now always convert things to Kelvin. Okay, convert things to Kelvin, and make sure that you're using the right number of significant digits when you do so. Okay, so again, we do this. Here's what I have. I have temperature 1. I convert to Kelvin, 288 degrees Kelvin. The final temperature, again, convert to Kelvin, 311 degrees Kelvin. The initial volume is this. What is the final volume? Apply Charles's law. Okay, so note the difference. So in this case, V1 is equal to BT1, and so our constant V1 T1 is equal to B, which is the same constant for V2 over T2. That's Charles's law. Okay, that's Charles's law. So volume 2 is now going to be equal to T2 over T1 times the initial volume. And just simply rearrange these to get whatever you want where you need it. You know, that's what we do. Plug in the numbers. 311 Kelvin, 288 Kelvin times the initial volume, 2.58 liters, and I get, again, plugging it into your calculator, 2.79 liters. Now, again, does that make sense? It certainly does, because as I increase the temperature, I get a bigger volume. If I decrease the temperature, I get a smaller volume. So always go back and check your data. Check your calculations. Simply, does your calculation make sense? Now, lastly, there's what's called Avogadro's law. And we talked about this already, and that is at constant temperature and pressure, the volume is simply directly proportional to the number of moles. Okay? So we have the volume of the gas is proportional. So we have Charles's law, so Avogadro's law, which is Avogadro. We can do the same analysis, is that volume is proportional to A, some constant times the number of moles. We have Charles's law says that volume is proportional to B times the temperature. And we have Boyle. It says that pressure volume is equal to a constant. Okay? So we can put all of those together into a single unified equation, and that says that pressure volume is equal to some constant N, which is from Avogadro, T from Charles, and some constant proportionality R. Again, here's our constant. This is our universal gas constant. It doesn't depend upon the nature of the gas itself. It is simply a number that converts pressure volume to temperature. N moles. B is a constant, and this is another constant. So our universal gas constant is what we want. So again, we can apply Avogadro's law if we wish, and we have so many moles of this, and I can find what is the volume occupied by so many moles of something else. In this particular case, we actually have a reaction that goes on. So what if all of the O2 in this case was converted to 0.33 moles of ozone, same T and P, what is the volume? Okay. Well, I have fewer moles present in the system, therefore I have a smaller volume, is what I should get. It should be something you can almost think this through very easily and make sure that we get the right number. So again, volume over number of moles is equal to a constant, and so therefore V1 over N1 is equal to V2 over N2, which we have here, and I can then use the same logic that we had before, plug numbers in, and I get a smaller volume, just as we heuristically figured out. If I have fewer gas molecules in the system, they must occupy less space, less volume. So again, we have all three of these guys we plug together, and we want a uniform unified theory, and that's what's called the ideal gas law. And there it is. There's the ideal gas law. It's specifically, it's if the pressure is expressed in atmospheres and volume is in liters, R is equal to, and the units are not right on this, unfortunately, in the PowerPoint, because I need to get joules really on both sides of this. We can figure out what the units must be, right? So R is some sort of constant. So let's just use my notation. This little bracket simply means what are the units: pressure, volume, temperature, and moles. So if I have it, this must have units of atmospheres, liters, Kelvin, and moles. So the R is in units of is 0.08206 liters, atmospheres, Kelvin, mole. Okay. I don't know why they don't. Maybe it just didn't occur. It didn't appear in the PowerPoint module that I received, but it's not in there. But this is the units that you need: liter, atmospheres, Kelvin, mole. Because I need to make sure that the units on this side of the equation are equal to the units on that side of the equation. Liters, atmospheres, moles times Kelvin, right? Therefore, all those units have to cancel out to get that. This is the ideal universal gas constant. It works for neon, helium, everything. But it is the universal gas constant. Now, it really isn't anything more than a conversion factor between energy and temperature. And in fact, you can write it out in terms of another constant is equal to the Avogadro number times the Boltzmann Boltzmann's constant. Okay, so it simply is the Avogadro number, 1 mole, and the Boltzmann constant. That is the ideal gas constant. Okay, so it's like I said before, it's an equation of state for a gas, and it's an empirical equation. It's based upon experimental measurements, but importantly, as I mentioned before, it is the limiting behavior of any gas law. Okay, so if I take the size of the atoms to 0, I get the ideal gas law. If I take the pressure to 0, I get the ideal gas law. And any gas that obeys this is said to behave ideally. Now, we can look at deviations from ideal gas, and that's important. If I look at, make a plot, so for example, of let's define some new number Z as equal to pressure volume over RT for 1 mole. Okay, Z equals 1 would be the ideal limit, and this would be at maybe pressure down here. So this would be the ideal limit. So Z equals 1, and I could have at low pressure, maybe my gas does this, and some gases they do this, but generally what happens is you get behavior that looks like this. This is called the compressibility factor. That's called the compressibility factor. This is the ideal limit. The dashed line is ideal. And these would be 2 examples of real gases. Might have some sort of positive or negative deviation between ideal behavior, but they'll always obey the ideal gas law at low pressure. Now, what is low pressure? Well, generally 1 atmosphere is about right here. So very high pressure, multiple atmosphere, I start getting severe deviations from ideality, and so this is so things are less compressible or more compressible than an ideal gas. It all depends upon the nature of the gas itself. And there are different equations of state that can explain this behavior. Okay, so an ideal gas law, but an ideal gas law is really, really important to know. So if there's one equation that you must memorize for this entire section, is this equation here, PV equals nRT. Memorize that equation, okay? I don't ask you to memorize too many equations, but that one you need to remember that equation. Okay, this is the ideal gas law. Pressure and atmosphere volume in liters, number of moles, ideal gas constant, temperature in Kelvin, okay? And know how to manipulate all of these. Now, all of the examples we have is simple algebra to manipulate the ideal gas law to isolate the term that we want. Because in the ideal gas law, it says that any ideal gas, this relationship must hold. Pressure times volume is equal to nRT. And so in other words, then this is an energy, that the energy of the gas only depends upon the temperature. Well, and the number, how much stuff that you have in the system. So again, here we can apply. It's a little bit more complicated of an example. So suppose I have a gas, argon. I have 0.35 moles at 13 degrees Celsius and a pressure of 568 torr. And I heat it to a new pressure and a new temperature. I'm going to calculate the change in the volume. So I'm going to change the pressure and increase the pressure and increase the temperature at the same time. And so here it is. I need to convert all my temperatures to Kelvin, make sure all my atmospheres are in, everything is in atmospheres. So I convert torr to atmospheres. So now I have everything I have in the right units. Moles, atmospheres, and kelvins. Moles, atmospheres, and Kelvin. Because my gas constant is in moles, atmospheres, Kelvin, and liters. Okay? So long as I have all those, everything in the right units, here it is, with the right units too. R is equal to, I need my volume in liters, pressure in atmospheres, temperatures in Kelvin, number of molecules in moles. Ideal gas constant. Plug it in. So right there, 11 liters. This is how much I started with. And now I can recalculate V2 because I now know V1. Okay, nRT V2. So I go from 11 liters to 8 liters in undergoing that change of state. So my change in volume is minus 3 liters. I've decreased the volume by 3 liters. Okay, so I'm going to end at that. We'll pick up the next time on Wednesday with a discussion of gas stoichiometry and how we can track chemical reactions by looking at changes of pressure, temperature, and volume as a chemical reaction occurs in the system. So again, subscribe for an extra point and do the little homemade barometer experiment. Send me the data in a picture, and I'll give you an extra credit point. I've got a number of extra credit points I can distribute, and this is simply maybe a little bit of way to bide your time and stay engaged with the class. So thanks for listening. Good luck with the rest of your course. Stay safe, stay healthy, and I will see you the next time.